So I've wanted to make some videos on reverse engineering for a while, and I started making intros to using GHIDRA, but I've been caught up, well, a couple things. I've been busy, but I've been caught up with the idea, trying to figure out how to go about making them. Should I do more an academic approach and show you how things are done in the compiler and how things map to the disassembly, or should I give you some theories on things? And eventually I realized that if I try to make this all perfect and academic, it will never get done. It reminds me of my brother-in-law. When I was trying to learn electronics, I tried reading academic electronic books for years, and I never got anywhere because I'd read something and it would kind of make sense, but I'd never do anything with it, and then I'd forget it, and it didn't make any sense. And he just said, just start messing around with it. And sure enough, after like 7 years, one day I just started messing around, and it just came together, and everything started to make sense. And I just learned more that way. So I'm going to approach this in that manner. I'm just going to start giving samples and start disassembling them. So I've decided to use, at least to start off with, some of the examples on the Exploit.education website, which is a website of challenges that for people who want to do hacking or exploitation, or I think it's designed for people who play in CTFs, I'm not sure, but they have some examples up there, and I thought they would be very useful because they start out very simple, and also people seem to be interested in the information on seeing how to solve those. So I thought, hey, kill two birds with one stone. So we'll go ahead and just start doing those. So I'm going to go ahead and start it up. So I've stored the files in my desktop. I'm sorry, not on my desktop, on my computer, in Exploit.education. And then there's I'm going to start with, I think they call it the Phoenix examples. So yeah, so I did at the Exploit.education Phoenix AMD 64 download. And then what I did actually is I also, so it's a QEMU image that you can start up. All you have to do is type boot Exploit Phoenix AMD SH, and it starts out a virtual machine, blah blah blah. But I wanted to grab the files because I'm going to use the files and reverse engineer them. So I just mounted the QCOW image to my machine and copied off the files, and I stored them in files in here. I'm going to go ahead and close this down because we don't even need to see this right now. Actually, I'll just minimize it, and I'm going to go ahead and minimize that window. Open up another terminal. CD Exploit.education, CD, yep, CD files. If we go to Exploit.education and click on it, we click on Phoenix, it actually shows you the different exercises. It tells you getting started, what to do, or information about getting started, how to log in, and all that. And the first one is stack 0. Now, it actually gives us the source code. What they want us to do is get the program to, when you run it, to do something special. But I don't even want to look at the source code because the purpose of this is not to actually do the exploit, which we will, but to or do the challenge, but to actually just reverse engineer software. And so let's not even look at the source code. GHIDRA is going to give it to us anyway, basically. So let's start up GHIDRA. We just type GHIDRA run, assuming you already installed GHIDRA. Create a project, new project, non-shared. We already have the directory. We'll call this one project's name stack 0. Add the file, and there I already have this in the directory and where I store those files. It's the file stack 0, and click OK. Click OK again, and then double click. And GHIDRA is going to start up, and it's going to do its thing. It says stack 0 has not been analyzed. You want to analyze it now? Yes. We choose the defaults. Click analyze, and it looks like it's done. So remember, C programs start with a function called main. So we double click on main, and oops, my listing window is gone. Let's get the listing window back. Okay, so there's the disassembly, and we see we also have the decompiled code, which if you actually looked at the source code on the website is very similar. So I'm going to actually do this two parts. First, we're going to look at the C because that's easy, and then we're going to look at the machine code. So I'm also, because I think it's very helpful to visualize this, I'm also going to pull up the function graph, and I will probably just make it small right now. Oh, here's the minimal function graph. Well, what the I do hate GHIDRA's user interface. It's kind of lame. Alright. So here you see actually the function graph is made up of what's called 4 basic blocks. So here we have an important term, basic block. And Wikipedia explains basic blocks pretty well, so I'm just going to read the Wikipedia entry. Basic block is a straight line code sequence with no branches in except the entry point and no branches out except the exit. What that means is once you get in a basic block, you're going to do every single instruction in that basic block, and then you're going to go through one of 2 paths to get out of the block. So once you enter a basic block, you will do every instruction in that basic block. Basically what I said, once we get in, we have no branches. It's just going to run one piece of code after another until we branch. Okay, and then we go to another basic block. So compilers build programs out of basic blocks. Okay, and it's nice to see that. So we have a basic block here, basic block here, basic block here, basic block here for this function called main. So let's look at the code. And GHIDRA has done a great job of turning this code basically back into the original C. What we have here is we have a character array, local 58, and it's already determined that this is a size 64, and then an integer, local 18. Now I like to rename variables once I have any idea what they are, so we'll go ahead and do that once we do. So then it prints out to the screen, welcome to Phoenix Stack 0, brought to you by HTTPS Exploit exercises. Sets this value local 18 to 0. Then it reads in input from the keyboard and stores it as local into the variable local 58. And then if local 18 is 0, it does one thing, otherwise it does another thing. So what do we know here? Well, this is interesting. The choice of how to move, I do not understand why. There we go. The choice of how to move is going to be based on whether to go down this code path or this code path. Is going to be based on the value of local 18. If local 18 is 0, then it's going to do this, otherwise it's going to do this. Let's rename this local 18 to we'll call decision variable, because the decision is going to count be based on this. So you see everywhere that was, it renames it, and well, look at this. Decision variable set to 1, it's never changed, so theoretically it should always do this code path, right? It should always go and say, oh, change me has not been changed, would you like to try again? But the exercise actually wants you to try to actually get it to go down this path. And, well, how does that work? That's interesting. Well, I will show you that, but first, now that we've looked at the code in the decompiler, let's actually analyze this code as disassembly. So let's assume we'll just minimize this. Can we minimize that? We'll just kind of make it, oh yeah, we'll just close the decompile window. Okay, so now let's look at the code and let's bring out our function graph, because when looking at the code as machine code or assembly code, it's often easier to have the function graph there. And I don't know why it's not resized. I'm trying to resize this thing. It's not letting me resize it. I've never had that problem before, but oh well. So let's look at the code. We have main. It's our enters. We have undefined stack minus 18 decision variable. It shows you where on the stack the variable starts. Negative 18 of where the stack frame is. It and then the size is 4. Okay. And it says it's undefined 4. Let's change that to int. I like to change everything from undefined to what it actually is. So to change the type, it's Shift L. And of course, it's not going to let me do it. Why doesn't it let me do it here? Am I going to have to do it in the listing view? Maybe I do. Set data type. Right click, set data type to int. There, now it did it. Good. Except I set the wrong one. So let's undo that. Here we go. Set data type to int. And I can set it to float. Set data type to, let's try this again, int. There we go. Okay. And then we have undefined here, undefined one stack, negative 58, local negative local 58. Well, we'll worry about that later. All right. So what do we have here? First, I wish my scroll button worked. There we go. So first we have push RBP. So that is part of what's called the function. So we have another important term. This time it's the function prologue. What the function prologue is it's some code inserted by the compiler that sets up some housekeeping. Generally what it will do is it will back up registers that need to be saved in that function, that is, registers that are going to be overwritten in the function. It's going to set something called the frame pointer if a frame pointer is used, and the frame pointer points to the top of what's called the stack frame, and then it's going to subtract from the stack pointer, not the frame pointer, space for the storage of the local variables. So in Intel x86 or x86-64, the function prologue usually it looks like this. Prolog. A couple things that always happen before the code of any function is called. The first thing you do is, if you're using a frame pointer, you push the old frame pointer onto the stack. Then you move the current stack pointer into the frame pointer register. Okay, and then you subtract the number of bytes you need for local storage. So here we are from the stack pointer, which points somewhere in memory. We're going to subtract 60 hex bytes, which is what is that, 96 decimal, and you can actually see that if you just hover over it, does say byte 60h equals 96 decimal. Okay, so that means that tells us something. We know that this function is going to use 96 bytes for local variables. Okay. Now what's it doing here? It's moving this register's contents to RBP local 5C. So local, and 5C is hex. That means where on the stack or relative to the frame pointer will this be. So it's actually RBP. It's the address of RBP plus 5C. Okay, and what that actually is it's not really plus 5C, it's minus 5C. So RBP minus 5C, that address, at that address it's going to store EDI. So what does that mean? Well, I'm renaming this variable. I'm going to rename this, if it's going to let me, rename function variable. I'm going to call it, rather than local 5C, I'm just going to call it EDI backup, because we know it's going to be backing up EDI. Okay, and as you see here, it changes in the stack view here. It says the stack pointer minus 5C, and it's 4 bytes long, is actually the variable name EDI backup, basically. Okay, and then it's going to do the same thing for RSI. It's moving the contents of RSI into RBP plus local 68. So we're going to go ahead and EDI is a 32-bit register. That's why we see move D word pointer. RSI is a 64-bit register, so that's why we see keyword pointer. Okay, so we're going to change this RSI. We'll change the name. I'll hit elf, change the name, rename function variable, and we're going to call this RSI backup. Okay, which what does that mean to us? Why did it do that? Well, because this means that the registers EDI and RSI are going to be used in the rest of the function. So whatever they were holding before, we eventually want to probably have that back at some point when the function is over. So what the function prolog does is it does this push RBP, move RBP, RSP, and then it subtracts from the RSP, the stack pointer, enough for the local variables. Then it usually backs up the registers that it is going to use in the function, so that later on we'll actually restore them back. So when the function returns, all the registers are back. Now that's not true of everything there. Depending on the calling conventions, some registers are expected to remain when you do function calls. You can expect that those registers, when your function call is done, will still have them, and some registers are defined to not be saved. That is, if you want, when you're calling a function and you're writing the disassembly, if you want those register values to remain after function calls, you will have to back them up yourself. But EDI and RSI are ones that we have to return back to the state that they were in based on this calling convention. Don't worry too much about that. Anyway, then we're going to move EDI into EDI the memory address where this string welcome to Phoenix stack 0 is. Okay, and that's at memory address 400680 in hex. Okay, then it's going to call puts, which is puts takes a string and actually prints it out. Now, why did we move it in? Why did we move this function or this string, the pointer to the string into EDI, because that's what the calling convention for x86 on Linux requires. That means that the first argument to a function needs to be stored in EDI. Okay? So it does that, then it's going to move the value 0 into the local function variable, decision variable. Okay, again, RBP, why do you see RBP? Because RBP is what's called the frame pointer, and the local variables, as well as any stack or function parameters that were pushed on the stack, are going to be referenced relative to RBP. Okay. Then load effective address. We're going to take the value of RBP plus -50, and we're going to store that in RAX. And it's telling us here, GHIDRA is doing some help for us. It's actually telling us that when this is done, RAX will actually hold the value of the variable local 58. And we're going to rename that because, well, we know from the disassembly that local 58 was actually that string. So we'll do the input data. Okay, so we'll label that input data. And then we move RAX to RDI. Call gets. Gets is going to read from the keyboard and store the value into the memory pointed to by RDI. Again, RDI or EDI, it's the first parameter to a function. REI and EDI are actually the same register. It's when you refer to it as RDI, it's the whole 64 bits of the register. When you refer to it as EDI, it's the low 32 bits. Okay. So then we are going to move the decision variable value, so the frame pointer plus the offset, the decision variable, so it's a -18 hex bytes. Whatever is an RBP plus -18 bytes, D word, that's 32-bit value, is going to be moved into the register EAX. Okay. Then we test EAX to see if it's 0. So test, when you do a test on something, it actually does a subtraction and subtracts one from the other. So test EAX, well, if you subtract, I'm sorry, made a mistake there. It doesn't, I was thinking of compare. Test actually does a bitwise AND of the two arguments together. So EAX by EAX, if any of these, when you do a test of something by itself, if that's actually checking to see if it's 0, because if any bits are set, the result will not be 0. But the only time it will ever be set is if, or only time all bits will be 0 is if all bits are 0. So basically, it's checking to see if they're 0. So it tests, and then it sets the condition flags. So it sets basically we're saying, is EAX 0? And then if it is 0, JZ jump 0 to this code, okay, to this code lab where it's labeled lab 40061C, and that's the memory address. Okay. So we're going to label this. I'm going to hit L, and we're going to do if decision variable, maybe I'll put it under, is 0. Okay. And this is where we see now, if we look at the code, this is where we take two paths. If the decision variable is 0, it's going to jump down to this code. It's going to say, uh-oh, change me has not been changed. Let me see if I can make this wider. Yeah. Okay. That's not what I wanted, but anyway. Okay, and then it's going to print that out, and then it's going to jump to the next state part, which is right here. Which I'm just going to go ahead and rename this exit, or this is actually going to be done. We'll name it done. Okay. Then it moves EDI into 0 into EDI and calls exit. This before when you an exit is a function call. EDI is a parameter, so it's actually setting the return value of the program to 0. Okay. If when we tested the decision variable, if it was not 0, then it would have jumped. It would have actually not jumped. It would have went to the next code and moved into EDI, the pointer to the string. Well done. The change me variable is changed, and then call puts, and then jump to done. Okay. So that is reverse engineering that program. Now, we're wondering, if you're interested in the exploit component of this, well, how is it possible that, and we'll bring back the C code, the decompiler. We know we set decision variable to 0 and we never change it. Well, how does that work? Why would we ever hit this code? And normally we shouldn't. However, there is a bug in this program. When it get_s will read as much data as you send it, and when you, well, basically until you hit a new line. So as much data as you type before you hit a new line, and it stores that as input data. What happens is input data is only 64 bytes. So if you add more than 64 bytes, it spills over into the next variable, which is decision variable. So decision variable here and input data here, when we store into input data, it's gonna the first variable, the first character is going to be stored at stack minus 58, the second will be stored at stack minus 57, so forth and so on, and we're actually working our way up, and eventually we'll overwrite decision variable. So because GHIDRA is cool, it actually told us how big input data, how much it could hold. So we know we have to we need to put more than 64 bytes in. However, we also could have just looked at where these variables are stored in the stack and did some math. Okay. Oops, that's not what I wanted to do. I want to pull up GNOME, or calculator will work, yeah. And we want programming mode, and we know 58 is the beginning of input variable, it's negative 58, and then minus 18, oh, but we want to put this in hex, not decimal. So 58 minus 18, that's 40 hex 64. So if we didn't have the decompiler that did this for us, we could figure out how many bytes of data we needed to override by just looking at where this variable begins and where the next variable begins, which is decision variable. So now let's actually try that in the program here. And why is key mode dead? That's interesting. To log in, user, and I believe the password is user. Then we go to opt, Phoenix, AMD, and we want to run stack 0. It'll say welcome to stack 0, brought to you by blah blah blah. We put in something. If we only put 3 characters, it'll say, oh no, change me has not been changed. Would you like to try again? Run it again, and this time let's add we need more than 64. We need 65 at least, because there's 64 bytes of storage available in input data here, and we need to go we need to actually write something that's not 0 in a decision variable. So 0, 61, 62, 63, 64. Now if we do exactly 64, it should not work. See? And right, it did not work. So let's do it again, and then we'll just do okay, so let's add an extra byte, and boom, well done, the change me variable has changed. So there you go. There's your first example of using GHIDRA for reverse engineering. And we also solved the Exploit.education Phoenix Stack 0 problem.